Hi everyone, our topic today is scenario sensitivity and simulation analysis. Let's go directly to the map to figure out where these topics fit in with our narrative for the semester. I think at this point everybody's sick of me outlining our official technical definition of finance, so I'm going to forego that. Simply going to point out that in our last few lectures, we've been focusing on buying and selling fractional or entire ownership of assets and the go, no-go decisions, which both fall under the category of optimal deployment of financial capital. There's been, I hope, a common theme that we've identified in both of those topics, whether it's buying and selling fractional or entire ownership of assets or the go, no-go decision. In both of those cases, what we're typically trying to do is value a set of expected future cash flows and then contrast that value against either the cost. So that's the essence of NPV, right? Net present value is thinking about the cost of a project against the present value of the future cash flows that it's going to generate. Or if it comes to buying and selling an asset, we're thinking about the value, the present value of those expected future cash flows, and we're contrasting that against a market price, which can also be thought of as simply the cost of the asset. So whether it's a go, no-go decision or buying and selling assets, what we're generally doing is we're finding the present value of future cash flows and comparing that to a prevailing market price or cost. The common theme then, of course, is that the value in either of those situations, the value is simply the sum of the present value of the expected future cash flows. But this leads to a lingering problem. And I think George P. Box, who is a famous statistician, has said it as concisely as I've ever seen. George P. Box said, all models are wrong, but some are useful. What he's getting at is whether you're buying or selling assets or whether you're calculating NPV and IRR, we are relying on models. We're relying on quantitative frameworks to give us outputs that then inform our decisions. So these are models, these quantitative frameworks. And every single one of those models that we're going to employ, whether it's a dividend discount model, a discounted cash flows model, a residual earnings model, whether it's pricing a bond, whether it's NPV, all of those models are going to be wrong, but some of them are useful. Well, why is it that all models are wrong? Well, if we think about it, all of the outputs that we get from those various models are highly sensitive to the inputs. And most of those inputs are a matter of forecasting. If you think about it in the dividend discount model, you have to make a forecast about how rapidly you believe the dividends will grow. When you do a net present value calculation, it involves a ton of inputs that orbit around the idea of forecasting. How quickly will the cash flows grow? Of course, determining how quickly the cash flows will grow usually requires forecasting the income statement and the balance sheet. So the bottom line is all of these outputs are created through models that involve inputs, and those inputs typically involve forecasting, and we know that anytime we forecast, there will be forecasting error. It's inevitable. So because of that, because of the problems with forecasting and model sensitivity to the forecasted inputs, we know that often whatever we get as the output to a model is going to be wrong. And that leads to a massive warning. So the warning that I want to give you is never make a decision based on a singular output derived from static inputs, especially if those inputs involve forecasting. So what we want to do today is talk about tools that we can implement that will provide greater richness and robustness in the information that our models give us. I want to remind you, I've tried to be emphatic about this point. The models that we learn, whether it's NPV, IRR, discounted payback period, DCF, residual income model, dividend discount model, whatever model we're implementing, you would never ever make a final decision based solely on that model. The models are data points that should inform your decision. So what we want to do is now add some richness and some robustness to expand the vastness of our information set so that we can have more information, better content for making decisions. The three tools that we're going to talk about, we're going to begin with the simplest and then sort of increase in complexity. So we're going to start with scenario analysis. We'll move to sensitivity analysis, and we'll finish with simulation analysis. So let's launch right into scenario analysis. The intuition behind scenario analysis is very straightforward, and also executing scenario analysis is fairly straightforward. The intuition is that static inputs only consider a single possible future state of the world. So in other words, when you do a model and you put in your inputs, what you are saying is there is only one possible future state of the world, and here it is based on my inputs. However, it is wise to consider that there are numerous other possible future states, and we'll call those scenarios, and we should at least try to contemplate some of those alternative states of the world. So how do we operationalize scenario analysis? Again, this is very easy. You don't even need me to lecture on it probably. But at a minimum, you should ask yourself about 3 different scenarios. And the 3 different scenarios would be the base case, and the base case is your very best guess at how the future is going to unfold. In other words, to do the base case for your inputs, you should put in the variables for your inputs that you think are most likely to be realized. Next, you should consider the worst case scenario. The way we think about the worst case scenario is assume that all of the input variables conspire against your project and investment. So for the worst case scenario, you should use as your inputs the numbers that would be the worst case scenario for the output that you're considering. So for instance, in an NPV calculation, what would make for the lowest NPV? Well, that would include low growth rates for your company in terms of forecasting earnings and cash flows. That would also include a high discount rate. So in a worst case scenario analysis, you should have low growth rates, lower cash flows, higher discount rates, and you should also ratchet any other input variable in the direction that handicaps or lowers your output. Lastly, you should entertain the possibility of a best case scenario. So this is the exact opposite. So for all of your inputs, you're going to consider what could feasibly, realistically be the best case for each of these input variables, and you would put that into your analysis. So I just want to show this to you very quickly, very easily, and in order to do that, the setting that I'm going to call upon is the solar panel example. You remember that last class I had you calculate the net present value of putting solar panels on my house. Forgive me if this is slightly different than what you did. Sometimes these numbers are changing a little bit as I tinker with things. But here's essentially the problem. You remember I was considering putting solar panels on my house. The initial cost was going to be about $31,000. There were going to be some federal and state tax incentives that were going to significantly reduce the net cost to me. We didn't worry at all about financing options. We just said that we would pay for this in cash. And then down here are some of the really key input variables for our analysis. If you remember, one of those really important input variables is how much electricity will these solar panels generate in the first year. So we estimated 13,874 kilowatt hours. The way that we got that was that I use slightly over 14,000 per year, and Isaac Freckleton in his presentation said that these solar panels would generate 99% of that in a given year. So that's the first year kilowatt hours produced, but we also said that there's an annual efficiency reduction. So what we mean by that is every year the solar panels will generate slightly less electricity. The degradation factor that we used was 0.457%. I based that on the research that suggests that after 40 years, the solar panels that were installed in the 70s have been about 80% efficient. So that's an important input variable, very important to our analysis. Another key input variable for us is how much I pay per kilowatt hour that I use. Right now I pay about 12.4 cents for each kilowatt hour that I use. We know that Rocky Mountain Power has a tiered pricing system, but I'm just going to go ahead and use this average. It keeps the math simple for us. Another important input is the inflation rate in my electricity charge per year. So that rate tends to go up. Right now I'm assuming that it will go up at 4% per year. We're not going to worry about this input variable. It's not really that important. And then we said that there was going to be an annual increase in our homeowners insurance of about $100, and I just realized one of the shortcomings of my analysis is I don't have any way for this to ratchet up yet, so that's something I probably need to build into my model. Okay, we're also using a discount rate of 6.5%, but the way that I'm getting that discount rate is I'm simply taking the inflation rate and I'm adding 2.5%. Just a little reminder and preview, although we haven't talked about the theory behind estimating a discount rate, we did talk about how a discount rate is the same thing as a cost of capital, it's the same thing as a hurdle rate, and it's the same thing as a required rate of return. All of those things, generally speaking, have three components. Any required return has three components. The real rate of return, which is the return to a riskless asset if there's no inflation. The second component is inflation, the expected inflation premium. And the third component is the risk premium. That's compensation for the risk specific to the asset or the project. So all I'm doing is I'm taking my inflation rate 4% and adding a 2.5% premium. What that means is if I change my inflation rate, it's automatically going to change my discount rate. So those are the key inputs. What I've done over here is I've executed scenario analysis. In my base case, you can see that the inputs are exactly what I have here. But what I've done in my worst case scenario is I've said, well, what if the initial cost is more like 37,000 instead of 31,000? What if the kilowatt hours produced in year one are more like 13,313? And what if the inflation rate is more like 2.5% in the price per kilowatt hour? So these are all things that would conspire to make my NPV go down. Well, my NPV in this case ends up being 3,106, and my IRR ends up being 6.06%. In the base case, you can see my cost is 31,000. I actually have the kilowatt hours a little bit lower than what I showed you. It's 13,594, and I've got the inflation rate in the price per kilowatt hours at 4%. With those base numbers, my NPV is 8,466, and my IRR is 9.81%. In the best case scenario, I got a discount, which reduced the price down to 25,000. Now we are getting 99% of my electricity needs produced in the first year, and I assume that inflation in the price per kilowatt hour would kick up to 6%. When I do that, I get an NPV of 13,270 and an IRR of 14.65%. Now, the joke amongst most of us that teach this is as soon as you execute your best case scenario, you should delete it and ignore it because it will not happen, and you should focus simply on base and worst case. Past evidence suggests that reality will be somewhere between what you put in as your base and your worst case. Most of us have a psychological bias when we're considering doing a significant project. We have a tendency to be overly optimistic in our projections, and that's why, because of that sort of psychological bias, reality will probably wind up somewhere between the base and the worst case. So this turns out to be very, very informative. The base case is a very respectable 8,466 NPV. Again, a very respectable 9.81% IRR. I'll tell you what's informative about this is even in my worst case, and I want to be clear about this, when we say worst case, what we mean is worst case with some sort of moderate probability. You don't want to be considering the scenario that has a probability of 0.001%. That probability is that you get struck by lightning, you die, or we have a massive earthquake along the Wasatch Front and we all die. That's like the 0.00001% worst case scenario. What we're talking about here is like, 5% probability. There's at least a moderate, non-trivial probability. In that worst case scenario that I think has a moderate probability of playing out, you can see that my NPV is still positive and my IRR is still respectable. It's not huge, but it's not bad. So what this tells me is, even in my worst case, this project feels like it might make sense, and that is informative. So that is scenario analysis, and if we wanted to, we could consider other scenarios. The reality of it is scenario analysis is helpful. You should do it, but we have a lot more powerful tools that will add deeper richness to our information set, so let's move on to those tools. The second tool is called sensitivity analysis. The intuition, again, is fairly easy to get our minds around. Most model outputs, regardless of what model you're using, are highly sensitive to a relatively small set of key inputs. it would be wise, since that's the case, it would be wise to try to quantify the sensitivity of the model to these inputs. So what we're saying is figure out which inputs really drive the output and then quantify exactly how sensitive the output is and then contemplate what are the realistic values for this input that we might see as the future unfolds. So in order to execute this, you just want to identify those potential key inputs, and then you want to re-estimate your outputs after perturbing each of the key inputs. And you want to perturb them individually and in coordination with perturbations of other key inputs. So if we come back, here is our original analysis. What I'm going to do now is I'm going to do some sensitivity analysis, and let's think about which of these variables might actually have the biggest influence on our output. So our output is NPV and IRR. So what do we think drives that? Well, you would begin with a theoretical conversation, but I'm going to just show you what I've already sort of contemplated. So first off, what if we get sort of a shock to the system in the first year? What if it doesn't produce 13,874 kilowatt hours? What if it only produces 13? So if it does that, you can see that there is a fairly significant impact on the NPV. So the first thing I'm going to do is sensitivity analysis focused exclusively on the sensitivity of my NPV to the kilowatt hours produced in the first year. I'm going to use what's called a one-way data table in Excel. So right here, I have written down a range of possible values for the first year kilowatt hours produced. Now, you could go in and you could manually do this. You could say 12,800, there's the NPV. You could record it. You could do 12,900, record it. That's a very laborious, unnecessary way to do it. If you just structure your table this way, again, this is a one-way data table, then right here, in the cell above where you want to show the values of NPV, in that cell right there, you're going to link it to your key output variable, which in this case is NPV. Click Enter. Then what you do is highlight the cell just to the left of that, include that cell, and then highlight all the way down. So what you're telling Excel is, right here in this cell is the output, and we're going to use all of these as inputs, and then in the next step, you're going to tell Excel what it needs to do. So once you've highlighted the table, come up here to Data, and then go to What If Analysis, click on Data Table, and right here it's going to ask you for a row input and a column input cell. What Excel wants to know is, for the rows and the columns, what input variable are we talking about? Well, this is a one-way data table that only has a column of input variables. So we would leave the row input cell blank, and we would simply figure out what these are the input variables for. Well, this column represents the input values for the kilowatt hours produced in the first year. So we would click on that as the column input cell. So again, we have a column of inputs, and they are the possible values for this input variable. When you click OK, Excel will automatically take each of these input variables, replace it in this cell right here, and then it will go to the NPV because you linked it in that cell. It will go to the NPV and record it right here. So we can see that it does have a big impact. As we go from 12,800 kilowatt hours in the first year up to 14,000, NPV goes from 6,400 to 9,000. So that's a pretty big swing. The good news is, even if it gets down to 12,800 in the first year, this is still a positive NPV project, so that's encouraging. But we also can do what's called a two-way data table. So let me show you a two-way data table. The next thing I've done over here is I've said, okay, yeah, let's figure out the impact of the first year electricity production input, but let's also combine that with the impact of the annual inflation rate in the price per kilowatt hours. So now what we're going to do is we're going to change two variables at a time, and we're still going to record NPV. The way that you do this is now you have to put NPV in the hinge point of the table. This is the cell above and to the left of all of your possible input variables. So I'm going to link that with net present value. Then I'm going to highlight all of these. So you can see I've highlighted both the row of possible input values and the column of possible input values and all of the blank cells where I want it to populate NPV. I come back up to data, what if analysis, data table. Now it says, well, I have a row of inputs. What variable do you want me to put those values in? Well, I want that to be the inflation rate in the price per kilowatt hour. We already know what the column input cell is. That's the first year electricity generation. If we click OK, the table will now populate with all of the NPV values. One thing you can do from this point is you can include some conditional formatting just to add some sort of color heat map properties to this. So you can highlight all of that, come back to the home ribbon, click on conditional formatting. You can do color scales, something like that, which gives you a bit of a heat map. So you can see right there it's red is the lowest values, green is the highest value. So obviously the higher the electricity production and the higher the inflation rate in the price per kilowatt hour, we get a higher value for our NPV. If we get low inflation in electricity and lower electricity creation, we get a lower NPV. But again, the usefulness of this is now I can see exactly how sensitive my NPV is to these variables, and there's something very informative here. NPV is fairly sensitive to the electricity created in the first year. You can see that it's the difference between 6,000 and 8,600 in NPV, but it's not very sensitive to the inflation rate in the price per kilowatt hour, at least in the way that I rigged up the model. Whether it's 1% or 8% inflation, it's only a difference in NPV of about $600 in this case right here. So what we can say pretty clearly is this model is much more sensitive to the kilowatt hours that get produced in the first year than it is to the inflation rate. The other nice piece of information from this analysis, no matter where I look on this heat map, the NPV is positive. I should mention that's a rare outcome, and that's a signal that you've got sort of a unicorn project. All right, so that's sensitivity analysis, very useful. We think more useful than scenario analysis, again, because it tells us which of the input variables really is driving that output variable, how sensitive is the output variable to that particular input variable, and it's giving us information about at what point the NPV perhaps goes negative or becomes unfavorable. Well, now we move on, we step up, ratchet up the complexity again, and we're going to move into the topic called simulation analysis. Here's the intuition. Sensitivity analysis is unambiguously tremendously beneficial, but it has some limitations in Excel. Specifically, as it stands in Excel, using the methods that I just showed you, Excel only allows for you to perturb two variables at a time. You can only do two-way data tables. There are no three-way data tables. Also, it's a little bit cumbersome to achieve a high level of granularity when analyzing a single variable. You can imagine if I wanted to get more granular with this inflation rate, what if I want to do 1.1%, 1.2%, all the way up to 10%? It's just going to be a lot more cumbersome. There's going to be a lot more cells involved. It's going to take more time. So for these reasons, we want to move on to simulation analysis, and I think you should view simulation analysis merely as sensitivity analysis on steroids. Let me march us right into the heart of simulation analysis. Operationally, here's how we execute simulation analysis. First off, identify your key input variables, the input variables about which there is uncertainty, and variation in those input variables will change the model output. Once you've identified those key inputs, the ones with uncertainty that drive the model output, we're going to replace each of those static inputs with the appropriate probability distribution. Once we replace all of those key input variables with probability distributions, Then we're going to estimate the model over thousands of iterations, allowing the inputs to change based on those probability distributions with each iteration. If you do that, you will literally get thousands of possible outputs. Take those thousands of possible outputs and draw a histogram of the outputs. Then use that histogram of the potential model outputs as further, richer, deeper, more nuanced information that you can use to make your decision. Okay, so I want to give you an example of this, but we need to have a really brief conversation, not a terribly deep conversation, about probability distributions. So here's a primer on probability distributions. A probability distribution is a graphic depiction of the possible outcomes of a random variable on the x-axis and the probability of each outcome on the y-axis. Just as an example, maybe our random variable is the number of points that the BYU basketball team scores in a game. So a probability distribution for that random variable, and it is a random variable, we cannot know beforehand how many points BYU will score in a game. It's a random variable. So we would put all of the possible outcomes on the x-axis. Then on the y-axis, we would put the probability of each of those possible outcomes, and we would draw a graph that connects all of those probabilities. I'll show you an example here shortly. Before we get there, let's just make a couple of notes. Note number one, if the probability of a specific outcome equals 1, then that means the outcome is certain. In other words, if you tell me that the probability of BYU scoring 61 points in a game is 1, which means 100%, then that means you are 100% sure it absolutely will happen. They will score 61 points. If you tell me that the probability of a specific outcome for a random variable is 0, that means it is an impossibility. It cannot happen. For example, the probability of BYU scoring -5 points is 0. It cannot happen. A few other notes: if you add the probabilities of all of the possible outcomes, they have to add up to 1. Also, the area under the distribution, under the graph, the area under the graph up to a certain possible outcome, that represents the probability of the outcome being equal to or less than that specific outcome. So if we actually did draw a probability distribution for the number of points that BYU scores in a game, then if you took the area of the graph up to 70, the area under the graph would tell you the probability of BYU scoring 70 points or fewer. The area to the right of that would tell you the probability of BYU scoring more points than that. And I should also add, I'm only going to expose you to one type of probability distribution. It's the normal distribution. It's the one that most of us are familiar with. And frankly, it's a very flexible, widely observed distribution in nature. So to show you the normal distribution, I'm going to show you the probability distributions of height amongst males and females in the United States of America. You can see that they both have a bell shape. This is the hallmark of the normal distribution. They are symmetric. And you can see that for men, the midpoint is right around 5'10". For women, the midpoint is right around 5'4" or 5'5". Okay, almost all distributions have what we call moments. There are 4 moments to a normal distribution. The 4 moments to the normal distribution are mean, standard deviation, skewness, and kurtosis. And each of these things help to describe the shape of the distribution. The mean, the statistical mean, is the midpoint. So if you drew a line right in the middle of this curve at about 5'9½", that is the statistical mean. And for women, it's right at 5'4½". That's the midpoint. The second moment, called the standard deviation, is a measure of dispersion. It tells you how wide the bell curve is around the midpoint. I'll show you in a second how to calculate that, but for now, just understand that standard deviation measures dispersion, the width of the curve. The third moment is called skewness, and it measures asymmetry. Some distributions have extreme asymmetry. An example of a distribution with extreme asymmetry is household income. The reason that it has extreme asymmetry is because it's truncated at 0. You can't make less than 0. Median household income is probably somewhere between $45,000 and $55,000 in America, but you can get massive skewness to the right side because household income can reach up to $1 billion or $2 a year. So you can imagine how that distribution would be massively skewed. The midpoint would be at about $50,000, but it would have observations reaching out into the billions. So that's the third moment, skewness. One of the hallmarks of the normal distribution is that there is no skewness. The normal distribution is a perfectly symmetrical distribution. The fourth moment of the normal distribution is called kurtosis. Kurtosis measures how thick the tails are. Most people don't pay much attention to kurtosis, and if it's a normal distribution, it has a static kurtosis, and so we don't get bothered about kurtosis. So what are the properties of a normal distribution? And this is very important. In a normal distribution, the entire shape of the curve, so the entire distribution, is entirely defined by the first two moments. In other words, the shape of these curves is 100% defined simply by the mean and the standard deviation. And the reason for that is there is no skewness. Skewness is 0, and kurtosis is constant at 3. So the tails don't have fat or thick tails. So because the normal distribution is such a frequently occurring, such a common distribution, and because it's the one that we're going to tinker with, and because it's only defined by the first two moments, let's make sure we understand the basics of calculating the first two moments of a normal distribution. The way that you calculate the sample mean is very easy. I know that this formula perhaps looks cumbersome, but it's not. All you do is add up all of your observations and divide by the total number of observations. So what this formula is saying is if xi simply represents the value of observation I, so maybe that's the 10th observation, and maybe that person that we're looking at is 5 foot 9 inches tall. Okay, 5'9", except you would measure that in inches, so you would say 69 inches. So you just take each observation and you add it up. So we would add up the height of everybody in our pool. Then we would just divide it by the total number of people that are in our pool. Calculating the standard deviation is a little bit more complex, but it's still not bad. Again, for each observation, you're going to record that observation. So for the person who's 69 inches, we would record 69 inches. Then what you do is you subtract the average. Over here, we calculated the sample mean. We call that x bar. So what you're going to do is you're going to take each observation and subtract the mean. Then you're going to square that. So let's say that the average is 70 inches. If we have an observation that's 69 inches, we would take our 69-inch observation, subtract our average of 70 inches, that's -1, and we would square it. That gives us a +1. You would do that for all the observations. For every single person, you would take their height, subtract the mean, and square it. Then you would add up all of those squares, the squared deviations around the mean, and you would divide it by n-1. Now, we're not doing a deep dive, so I'm not going to try to explain to you why it's n-1. Please just at this point believe me that that's the right way to estimate an unbiased standard deviation for a sample. But what you're doing here, don't get lost in the weeds. All you're doing is you're taking each observation, subtracting the mean, squaring it, and then you're basically dividing by the number of observations. So what does that represent? That represents the average squared deviation around the mean. Now, why do we need to square the deviations? Well, we want to know about dispersion. We want to know about dispersion around the mean. The problem is if you don't square it, they're going to wash each other out. If you have somebody who's 69 inches, 69 minus the mean is -1. But if you have somebody that's 71 inches and you subtract the average of 70 inches, that's a +1 dispersion. If you add -1 and +1, it equals 0. So your standard, if we don't square it, your measure of dispersion would say that there is no dispersion, but that's wrong. There is dispersion. If we have two people, one is 69 inches, one is 71 inches, there is dispersion around the mean. So the way to make sure that they don't wash each other out is to square them. So you take each observation, subtract the mean, square it. Divide by n-1. So that represents the average squared dispersion around the mean, and then we just take the square root of that. And so what does that leave us with? It's the average dispersion around the mean. So again, the way we calculate the average, add up the observations, divide by the number of observations, that's your mean. To get the standard deviation, take each observation, subtract the average, square that difference. Do that for each observation, add it up. Divide by n-1, that's your average squared dispersion. Take the square root of that and you have the average dispersion. Now, you might be sitting there saying, "Whoa, my head is starting to hurt. Why does this matter?" Let me show you why it matters. Before I show you why it matters, we need to make a little note. Oftentimes, mean and standard deviation will be referred to using Greek symbols mu and sigma. The distinction is that mu and sigma are supposed to be population statistics. X bar and S are sample statistics. But a lot of people use them interchangeably, so I'm not going to get worked up about it. Here's why all of that information matters. In a normal distribution, 68% of the observations fall within one standard deviation of the mean. So if you start at the mean and go back by one standard deviation and go forward by one standard deviation, 68% of the observations fall in that range. Roughly 95% of the observations are within two standard deviations of the mean. 99% of the observations fall within three standard deviations of the mean. So with a normal distribution, if you can figure out the mean and the standard deviation, and you go three standard deviations on either side of the mean, that represents your 99% range. 99% of the time, that variable is going to fall in that range. So let me give you an example here. The average male height in the US is 70 inches, with a standard deviation of 4 inches. What does the 68, 95, 99 rule tell us about the height of men in the US? Well, if we go three standard deviations on either side of 70 inches, so that means subtract 12 inches, so that would take us down to 58 inches, which if I'm doing my math right is 4'10", and add 12 inches, which if I'm doing my math right should be 6 feet 10 inches tall. So if we put all that together, the mean is 5'10" inches, the standard deviation is 4 inches, going three standard deviations to either side takes us down to 4'10" and up to 6'10". The 68, 95, 99 rule says that 99% of all men in the US should be between 4'10" and 6'10". If we just sort of do an eyeball test, that seems to me to be pretty reasonable. I don't know very many men that are below 4'10" or above 6'10". Now that we have a little bit of background behind us about probability distributions, I want to go show you how we can use probability distributions to execute simulation analysis. And again, we're going to use the solar panel example. So I'm going to ignore my sensitivity analysis that I just did. I'm going to hide that. So what I want to do is I want to identify my key input variables. And I would say definitely kilowatt hours produced is going to be a key input variable for me. I'm going to say that the annual efficiency reduction is another key input variable for me. And I'm going to say the inflation rate is another key input variable for me. So I'm going to use those three input variables. I'm going to replace them with a probability distribution. So instead of using a static 4% for my inflation rate, I'm going to replace that with a probability distribution. I'm going to use at risk, and you can see that right here up at the top I can insert a function. And it says, what type of function do you want? Well, I'm going to use a common function and look at all of the functions that you can choose from. We're going to use our normal function. risk amp is going to ask us for those first two moments. What is the mean and what is the standard deviation? And I'm going to say, well, the mean is 4%. That's what I think it's going to be. And maybe I'll put a standard deviation in of 1%. Now, what does that tell you? If I put in a standard deviation of 1%, then the 68, 95, 99 rule tells you that 99% of these iterations are going to involve an inflation rate between 1 and 7%. 3 standard deviations below and 3 standard deviations above. At risk highlights that with a dark blue to tell me that that is now a probability distribution. Now, in a second, I'm going to add some nuance, but I just want to show you what we can do. The next thing you can do is you can go to the net present value, put your cursor on that, and say, add output. So click on this icon right here. The name doesn't really matter. I'm just going to click OK. And you can see that now that's highlighted with red and white letters. That represents my output. Then what I can do is I can come up and do a simulation. I'm going to do 1,000 iterations. I'm going to start the simulation. And what you're going to see is that Excel is going to change that inflation rate. So 1,000 times, Excel is changing my inflation rate based on that probability distribution. So let's make sure we're clear. What it did is every time it did an iteration, it changed the inflation rate, and it drew that inflation rate from the probability distribution. What probability distribution? Normal distribution, mean 4%, standard deviation 1%. And each time it changed that inflation rate, it recalculated net present value. Then it gives you this really useful output. This is the histogram of outputs. These are all of the net present values that came out in my 1,000 iterations when that inflation rate changed. Notice over here that the minimum value for NPV was 8,304. The maximum was 9,092. You can see that the average was 9,764. And what you can do is you can slide this bar and you can do this. So there's a 0.5% there. Let me go to a 0.5% here. So what that tells me is, remember, the area underneath the distribution has to add up to 1. We said that earlier. So if a 0.5% is out here and a 0.5% is out here, then what's left is 99%. So this represents my 99% confidence interval for my NPV. So this tells me that if inflation is going to be a normal distribution, mean 4%, standard deviation of 1%, then my NPV has a 99% chance of being somewhere between 8,475 and 8,965. I hope you're starting to see how valuable this is. It's really powerful in terms of giving you more information. Well, let's add some nuance to this. Here's the first nuance I'm going to add. Let's change the kilowatt hours produced, and let's turn that into a risk normal as well. So we're going to make that a normal distribution. I'm going to make the average 13,800, and I'm going to give it a 200 standard deviation. So let's go 3 standard deviations on either side of the 13,800, and that takes me down to 13,200, or it takes me up to 14,400. Okay, I've done that. How about annual efficiency reduction? Let's also turn that into a risk normal. We'll make the average 0.00457. So risk normal, 0.00457. And for a standard deviation, I'm going to say 0.001. Okay, all right, now I've got 3 different input variables, all normal distributions. I'm going to put my cursor back on NPV. I'm going to start the simulation again. So now what's happening? 1,000 iterations, and there are 3 different variables that are being changed. 3 different variables that have probability distributions. Okay, again, I'm going to slide this over and try to get sort of my 99% confidence interval. Like so. Okay, so I did 1,000 iterations. I'm very close to my 99% confidence interval. You can see that when I replace those 3 input variables, I remove The static input variables, I replace them with dynamic probability distributions. I allow Excel to do 1,000 iterations with each of those input variables being pulled from normal distributions with the parameters that I put in. We get 1,000 different NPVs, and you can see here's the range of NPVs. What's really valuable to me is that in the 99% confidence interval, so in my 99% confidence interval, the NPV goes from 7,200 to 10,000. So it's still positive NPV in almost all of my iterations. That's, again, unusual. That's making this sort of a unicorn project. Okay, so that's sort of the basics. That's sort of the basics of simulation analysis. The idea is don't let these inputs be static. Replace them with probability distributions, define the distributions, and then do a ton of iterations where each time it pulls from those probability distributions and then create a histogram of outputs. So that's the basic idea of simulation analysis. I want to give you a couple of extensions on this. Here's the first extension. You can add correlation between the input variables. Okay, so let me give you an example of correlation. I'm going to replace discount rate. I'm going to replace discount rate with a risk normal, and I'm going to say that the average is 6.5% and the standard deviation is 1.5%. Again, go back and check the inputs. Excel did it okay that time. But I know that there's a strong correlation between the inflation rate and the discount rate. In fact, when I first built the model, the inflation rate was a part of the discount rate. So what I can do is I can actually specify what the correlation is between these two variables. All you have to do is click on each of them. So click on the inflation rate, hold the control button down, click on the discount rate. Now come up here to where it says define correlations. Okay, so we come in here, we've got this wizard now, and what we have to do is just define the correlations. So in a correlation matrix, you're going to have the same rows as you will columns. So here's cell L21, that's my inflation rate. Here's cell L21. The correlation should be 1, right? Those are the exact same cells, so the correlation is 1. Similarly, over here we have cell L27, that's the discount rate, cell L27. So in that box right there, the correlation is 1. What we have to define is the correlations of the off diagonals. What's the correlation between cell L27 and cell L21? We need to put that right here, so just double click on it. And I'm going to say that the correlation is very strong. I'm going to say that it's 75%, so I'm going to put in 0.75. Then you have to tell it where you're going to locate this correlation matrix. So you have to come over here and just click on an empty cell, because when you click OK, it's going to actually create a correlation matrix. So this right here becomes the correlation matrix. Now, when you start the simulation and it starts to change all of these numbers, not only is Excel going to make it so that your inflation rate ends up being a normal distribution with an average of 4% and a standard deviation of 1%, and not only is your discount rate going to end up having an average of 6.5% and a standard deviation of 1.5%, it's also going to be the case that those two variables will have a correlation of 0.75, so it will be very rare that those two variables would move opposite. So in the next iteration, in fact, maybe I should show you this. I'm going to go to Settings, and I'm going to click Random Values. So you'll be able to see these variables changing. And what you should see is that as inflation changes, the discount rate changes with it, and it'll go in the same direction most of the time. So can you see that? It changed. Inflation went up to 4.83. Discount rate went up to 7.3. So I'm going to do 1,000 iterations now that I've added correlation. All right, and we get our output. And once again, I'm going to sort of search for my 99% confidence interval, which is about right there, and my 99% confidence interval, which is about right there. So my 99% confidence interval goes from 1,250 up to 19,750, but notice now it's getting wider. Now the NPV is starting to approach zero. We've got a couple of outliers that do hit zero. So now it's becoming at least a possibility, given what we've done to our inputs, turning them into dynamic probability distributions, adding correlation. Now we are starting to get the possibility that NPV could go negative, although I'm still very encouraged that my 99% confidence interval includes all positive NPVs. So that is the first way that you can add nuance, is to simply add correlation. The second way that we can enhance our simulation analysis is to use past data to actually give us information about the right probability distribution to employ. If you remember, there are many, many types of functions we can use. When we said insert function, even looking at the common distributions, there are all sorts. There's uniform distributions, there is log normal distributions, there's Weibull distributions, there could be Poisson distributions. So there are all sorts of different distributions. Maybe what we used here for the inflation rate, if you remember right, previously we used a risk normal with a 4% average and a 1% standard deviation. Maybe that's the wrong distribution to use. So I'm just going to delete that completely. I'm going to delete all of what we did over here with correlation. I'm going to come back in here and get rid of the correlation. That's what's causing the problem there. So what we're going to do is we're going to go get past data on inflation. We're going to use that data to tell us what the right distribution is. Then we're going to redo our simulation. So I'm going to use what's called the Fred add-in, which is very easy to get. If you just Google download Fred add-in, it will pop up. And I'm going to do a data search. And I'm going to type in CPI, household energy, and I'm going to search. What I'm looking for is any component in the consumer price index that is associated exclusively with household energy. And if we find that, we're going to use that past data to give us some information about the distribution of inflation of electricity prices. So what I did is I found the variable, I added the series, then all I'm going to do here is I'm going to click A instead of M, that's going to be annual. Then I just come up here and click Get Fred Data. It's going to scrape the web for me. So what this is telling me on an annual basis, this is the value of the consumer price index associated exclusively with household energy. Well, I can calculate the inflation rate each year by taking this year's CPI minus last year's and dividing it by last year's. I send that all the way down. Then what I'm going to do is I'm going to highlight all of that data. I'm going to come back to at risk, and I'm going to click on distribution fitting, fit the distribution. I'm going to just simply click fit, click OK, and it's going to give me what it thinks is the best distribution to use. Now please notice the data that we highlighted, the actual inflation in the CPI index exclusive to household energy, is clearly not a normal distribution. You can see that it has skewness of 0.8927, and it's got kurtosis quite a bit higher than 3. At risk suggests that the best fitting distribution is this one, EXT value, and I don't remember exactly what that distribution is, but it shows you the red line is that distribution, and the blue bars represent the histogram of the actual data. If we think that that is the best distribution to use, we can immediately export that to the right cell by clicking on Write to Cell. So I'm going to click on Write to Cell, click Next. I'm going to come over here, and I'm going to click on the cell for the inflation rate and click OK. Once we've done that, we can now re-execute our simulation, and now inflation rate will no longer be a normal distribution. It's going to be this new distribution that better fits the past data. It's going to take a little bit longer because we're asking it to do something a little bit stronger. And once it gets done doing the simulation, again, I'm going to look for my 99% confidence interval, so I'm going to slide that back to a 0.5%, slide that out to a 0.5%, and you can see that my 99% confidence interval is 5,100 to 10,450. Again, all of those are positive. This is the Unicorn project. Okay, so what's the summary of simulation analysis? The basic idea is, instead of using static inputs that we know will be wrong, let's replace them with probability distributions. Let's do a bunch of iterations. Let's get thousands of possible outputs. When we get those thousands of possible outputs, let's look at the histogram of outputs. That's much richer information to help us make our decision than a single static output. And some of the enhancements that we can do to our analysis is we can include correlation between our probability distributions, and we can use past data to tell us the right type of probability distribution. Well, I hope you can see that simulation analysis is really, really powerful, only possible because of the computational technology that we now have at our fingertips. Remember, George P. Bach said that all models are wrong, some are useful. We happen to believe that the more we can use past data to help us determine the right probability distributions, to then replace our static inputs with, that then allow us to do multiple iterations, that then allows us to have a histogram, a graph of possible outputs, we think that gives you a much clearer and broader picture of how this might play out. Very rarely will you see all of the values in your 99% confidence intervals be positive NPV, but if you see that 90% of all of your outputs are positive NPV, that should give you some confidence in the project. If only 40% of your outputs are positive NPV, that should cause you to pause and consider the wisdom of the project. Well, I think that's all I want to give you for now. Talk more about this in class.